Resistivity of a particular material is related directly to its length, so how long it is, the length, and it's also related to the cross-sectional area. So what is the area, looking on the end of it? And just looking at this diagram again, in simple terms, resistivity of a material is the resistance of 1 cubic meter. So resistivity, the Greek letter rho, is the resistance of a piece of material which measures 1 cubic meter. In other words, this is 1 meter, this is 1 meter, and the height is 1 meter. That is a very large chunk if we're talking about copper or aluminium. So 1 cubic meter. Let me just try and explain that one step further. If we take an ohm meter, so there's our ohm meter, and I could connect one of the leads to this face, and I could connect its other lead right round the back to the opposite face, we would measure the resistivity of whatever this material is. Okay, so if this, for example, measured 10 ohms, and this measures 1 meter, 1 meter, 1 meter, 1 cubic meter, then this material has a resistivity of 10 ohms. Okay, so we just need to take that a little bit further. We'll do some calculations which will hopefully make this clear in a moment. The resistance of whatever material you're dealing with is dependent on 3 factors. The first one is the unique value for the material. There is a set value for copper, a set value for aluminium, a set value for tungsten, a set value for iron, and so it goes on. And we can find the resistance of any piece of material based on the facts that we've just discussed. We need to know its resistivity, the area, and the length. So from that, R equals rho L over A, and that will be in ohms. R equals rho times L divided by A, and that goes in the box at the bottom of your second page. Let's carry on with this. Let's continue discussing resistivity. So, as I said, all materials have resistivity, and if we take a cubic meter of silver, then the resistivity of silver is 16.4 times 10 to the minus 9 ohm meters. Silver is our best conductor. If we come down to copper, which is our most popularly used conductor because it has the right properties like malleability, flexibility, ductility, etc., then copper is 17.2 times 10 to the minus 9 ohm meters. Aluminium is good. It's not quite as good as copper for us, and that is typically in the area of 28.5 times 10 to the minus 9 ohm meters. So the lower the number, the better the conductor. And copper is still very good at 17.2 times 10 to the minus 9 ohm meters. Let us just discuss the way we use our numbers once more. And I want to pick on copper because it's our most popular conductor. And this is all about standard form and the multiples we use. So rho of copper, so resistivity of copper is 17.2 times 10 to the minus 9 ohm meters. I could rewrite that 17.2 times 10 to the minus 9, when we use the standard form and our multiples, is nano. So I could write nano ohm meters. These numbers are the same. Instead of writing 10 to the minus 9, I've used n. If we look at that from a different perspective, let's take the same number, and I could rewrite this as 17.2 times 10 to the minus 6. So I've made it 1,000 times smaller, the number. And if we're going 1,000 times smaller, then this becomes ohm millimeters. Hopefully that made sense. And likewise, if we're using 10 to the minus 6 here, we can allocate an appropriate letter. 10 to the minus 9 is nano. So this would be 17.2 times, apologies, not times, 17.2 micro ohm millimeters. Just have a think about what we've said here. All of these numbers are the same, but they're just written slightly differently. This is the most common way you will see it, but it's also quite common to see this if you get a calculation on this in your exams. Let's do some examples.